A mechanical wave is a wave that requires a medium to travel through versus an electromagnetic wave, which is a wave that can travel through nothingness, travel through space. Light from the sun travels through empty space. It's an electromagnetic wave. It's not a mechanical wave, but it still carries energy. A mechanical wave is something like a sound wave or a slinky wave or a water wave that requires a medium to carry that energy. There are two kinds of mechanical waves. Two kinds of these waves that travel through a medium that carry energy. They are transverse and longitudinal. You guys remember the difference between a transverse wave and a longitudinal wave? Travis? Yeah, which one is like that? Good. The transverse wave looks like this. This is the thing that we typically picture when we think of a wave, right? It's a sine wave. Where the particles, in this case, if the wave is traveling this way, Travis, wave is traveling to the right here, which way do the particles in this transverse wave move? What do we know about those particles? Yeah, they're moving up and down. They're moving perpendicular to the way the wave is traveling. What do we know about the motion of those particles? We know that it's perpendicular to the way the wave travels, right? We know that it's up and down, but how do we describe the motion of those particles? It's simple harmonic motion, yeah. We talked about simple harmonic motion for a couple of days. Simple harmonic motion is motion in which the restoring force is directly proportional to the displacement. In other words, it's motion that goes back and forth, back and forth, back and forth. Each of these particles on this wave go back and forth, back and forth, back and forth. This wave really is just simple harmonic motion, but it's simple harmonic motion a whole bunch of times. It's simple harmonic motion for each and every particle on that wave. So the wave itself is going to the right, but the particles are undergoing simple harmonic motion up and down. What do we call this thing up here? This bump in the wave? Really? Good, it's a crest. What do we call this thing down here, this dip in the wave? Right? Good, it's a trough. Good. Now we can label a couple more things. The amplitude of the wave. By the way, what's the amplitude of the wave related to? The bigger the amplitude, the bigger the wave, yes. The bigger the amplitude, the bigger the wave. So the amplitude would be the size of the wave as measured from the equilibrium position. We'd label it either here or we'd label it down here. This is a question, by the way, on your unit test coming up after Christmas. This exact thing. I'm going to ask you to label a whole bunch of things on a transverse wave. One of them is a crest, one of them is a trough, one of them is the direction of motion of the particles, one of them is the amplitude. Okay, this is exactly the question you're going to see on your test after the break. The amplitude is the size of the wave, as Lane just said. Now, it's related to what? If you have a bigger wave, you're out in the middle of the ocean, and you're bobbing up and down on a big, big wave, you know that that wave possesses more what? Energy. Yeah, it's a more energetic wave. Okay, you know that if you're on a little, just this little wave in a swimming pool or a little wave in a lake, okay, you know that there's energy in that wave. Waves carry energy, right? That's what they do. A little wave carries a little bit of energy. A big wave carries a lot of energy. If you're in that lake with a little wave and you're bobbing up and down, you know that there's a little bit of energy there. If you're in the ocean on a 5-meter swell going up and down, you know there's a lot more energy there. And it's a lot scarier because there's a lot more energy there. Okay, amplitude is related to the energy of the wave. Finally, we have one more term called the wavelength, given by this symbol lambda. Lambda is like an upside down Y. It's not really an upside down Y, it's a Greek letter, but it's like an upside down Y. Okay, where do we label the wavelength or lambda of this wave? Rucker? Sure, it can be, be careful with that last one. Crest to crest works, trough to trough works, anywhere over which the wave repeats itself. 0 point to 0 point doesn't quite work, Rucker, okay? Because that could be here, right? 0 to 0 is right here. And that's not the wavelength, right? That's, yeah. No, you're right. If you go from here to here, that's a wavelength because that's the distance over which the wave repeats itself. So anywhere where the wave repeats itself, that's going to be a wavelength. That's going to be lambda. All right, let's take a look at the longitudinal wave now. That's the one where we have this series of compressions and then rarefactions. Areas where we have high density and low density. What's this area right here called? Where we have a high density, where it's compressed. Travis? We call it a compression. Good. What is this area right here called that leads and follows the compression? That's the area where it's stretched out a little bit, right? Where the density of the wave is a little bit less. What's that called? Right? It's called a rarefaction. R-A-R-E, not refraction. Okay? R-A-R-E, rarefaction. Make sense? If we plotted the graph, we actually plotted a graph of density versus position here, then we would find the graph would end up looking like this. That's not the wave. That's a graphical representation of the wave. But it's kind of interesting that if we take a look at a graphical representation of density versus position of this wave, then it ends up forming a sine wave just like the transverse wave did. Give an example of a transverse wave. Where do we see a transverse wave in, not necessarily in everyday life, but in common life? Yeah. No. No, not a sound wave. Where do we see a transverse wave? The most common example of it is the thing that we picture as waves all the time, which is water waves, right? Waves in the ocean. Okay, those are more or less transverse waves. Longitudinal waves, the perfect example of a longitudinal wave would be the sound wave that you're listening to right now. We talked yesterday about transverse versus longitudinal and when we can have one, when we can have the other. Transverse waves can only be produced in a solid. Now, it doesn't mean you have to have a transverse wave in a solid. Longitudinal waves can be produced in a solid as well. But transverse waves can't be produced in a gas and a liquid. Does anybody remember why? If you have a wave in a gas or a liquid, it has to be longitudinal. Why is that the case? Well, that's true, actually. Yeah. Remember, we also said yesterday that a water wave, that's a good point. A water wave is actually kind of a combination of a couple of different things going on. So it's when we approximate it, we say it's a transverse wave. That's not quite true. There's some swirling motion going on underneath. But it looks like a transverse wave, right? And it's almost a transverse wave. Yep. Go ahead. Why do we not normally have a transverse wave in a liquid or gas? Yeah, yeah. We saw the slinky waves yesterday, right? And the slinky, when the slinky wave, the transverse slinky wave went from one end to the other, went from my hand to Bailey's hand. Okay, we saw that the particles are going perpendicular to the way the wave is moving. The only way that these particles can be pulled up to produce a big amplitude perpendicular to the way the wave is moving is if the particles before and after are connected to them. And that doesn't happen in a liquid and a gas. So if we want a transverse wave, a true transverse wave, we want to have a solid there. Okay, again, in a liquid or gas, we got to have longitudinal. In a solid, we can still have longitudinal, but we can also have transverse. Yeah, question?
In the liquid, where you say it's like a transverse wave,
yep.
More like one. Because
why?
The trough, there's particles missing underneath there, so that collapses down to fill that.
Yep.
Or there's excess particles that goes up and compressed.
Yeah, that's true. Yeah, and then let's say it's not a true it's not a true transverse wave when we're talking about a water wave. Okay, as I said, there's other things going on there as well. If you take a look at underneath the crest, you'd actually see some swirling motion of waves. So there's a whole bunch of little things going on. We see it as a transverse wave. Okay, it looks like a transverse wave, and it is almost a transverse wave. But as I said, there are some other things going on. Rucker, it's a good point. That's happening as well. But in the end, the point that I want to make with that is, that's what we see it as. That's what it looks like, right? Is a transverse wave. Yeah. Well, that's a good question, Travis. Travis just said, if you didn't hear it, when you have a compression or a rarefaction in a longitudinal wave, are the particles moving faster than in other words? Let's remember, first of all, that the particles in a wave aren't moving from the source to the observer, right? When you hear my voice right now, okay, the sound waves are causing your eardrum to vibrate. but it's not particles of air that are coming from my voice to your ear causing causing your eardrum to vibrate. Okay, it's particles right here that are in front of my vocal cords that are causing the particles in front of them to vibrate back and forth, which are causing them particles in front of them to vibrate back and forth. So the particles aren't traveling this way. The wave is traveling this way. But the individual particles within that wave are traveling back and forth. Now, from one part of the wave to the other, is there a difference in speed? Absolutely. Absolutely there is. Okay? We know that the further away from the equilibrium position there, this is simple harmonic motion, right? So the further away the particles are from being in its normal position, from the uncompressed or the unstretched state, the further they are away, then the bigger the restoring force is going to be, which is going to mean that they're going slower. Okay? As they go back through the equilibrium position, in other words, as this part of the wave and this part of the wave go back through the equilibrium position, they begin to speed up, speed up, speed up, speed up. As they go through that equilibrium position, they then begin to slow down, slow down, slow down. So they do change speeds. Absolutely, they change speeds within that wave motion. Now, with the particles here be moving faster than the particles here at the same time, no, they would not. Because the equation that describes simple harmonic motion, F is equal to kx. Okay? The restoring force acting on the particles here, the particles that are compressed, the particles themselves aren't compressed, but you know what I mean, the density compression. Okay? It's compressed by the same amount as it's stretched here. So if the displacement is the same here and here, just one is compressed and one is stretched, then the restoring force is the same, and the speed would therefore be the same as well. Does that make sense, Travis? No. The particles here are traveling at the same speed as the particles here. Now, at a different phase in the wave, they can be traveling at a different speed. Does that make sense? Okay. Speaking of speed, two equations that we use to describe the speed of a wave. The first one is the very first equation we learned this year, V equals d over t. Waves travel at a constant speed, right? The second one, this is the new one that we learned yesterday, V is equal to F times lambda. What did F stand for? Frequency, yeah. And what does lambda stand for? The wavelength, the length of the wave. If we multiply F times lambda, then together, then we're going to get speed. Good? Okay. We had 10 questions for homework last night, page 410. Any issues with any of those 10 questions on page 410 that we had last night? Number 9, okay. Any others? 10, 9 and 10? 9 and 10, any others? Going once, going twice? 9 and 10 it is. All right, number 9 says 2 tuning forks are generating sound waves with a frequency of 384. The waves from one tuning fork are generated in air with a speed is 350. The other is 1500. What's the speed of the sound in air, in water, and would you hear the same musical note underwater as you did in air? That's a good question. Let's copy that over so we have a little bit more space to work. Let's look at question A first. In question A, we have a frequency of 384 hertz. We have a speed in question A of 350 meters per second, and we want to find the wavelength. V is equal to F times lambda. Lambda is equal to V over F, which is 350 divided by 384. Somebody have that value? 350 divided by 384? Hayden? 0.091 meters. All right, let's find the wavelength in question B now. Lambda is equal to V over F. This time, V is not 350. This time, V is 1500. F is 384. What do we get for the wavelength here? Okay, sorry, not 0.091, but 0.91. Thank you. Hayden, do you have this one as well? 3.9. Okay, thank you. Let's go 3 digits there, actually. 3.9. We should have went 3 digits for the first one as well, right? Whatever. Close enough. Should be 3 digits, okay, guys, but they're going to be pretty much the same numbers as those. So big difference in wavelength, obviously, and the big difference comes from the big difference in speed. Okay? Waves travel faster in one medium than they do in another. They travel a lot faster through water than they do in air. How many people have ever seen the movie Stand By Me? It's an old movie. Good movie, though. Guys, you remember the scene? Those of you who have seen it, do you remember the scene where the boys are walking along the train tracks and they want to walk through this tunnel in the train? They put their ear down to the train tracks and they listen for the train coming. Kind of backfired because they walked into the train tunnel and there was a train coming anyways. Why would you do that? Why would you put your ear down to the track to listen for the train? Why wouldn't you just kind of do this, listen into the tunnel for the train? Yeah? Yeah. Steel carries sound a lot faster than air does, just like water carries sound a lot faster than air does, because the particles are closer together, you get more collisions between the particles. Longitudinal waves will travel faster in more dense media than they will in less dense media. And so the idea of putting your ear down to the track is that you're not going to hear the train any better through the track than you hear it through the air. You're just going to hear it sooner when the train is further away because the sound has traveled faster. Okay, so it does change the wavelength. Let's look at question C now. Would you hear the same musical note underwater as you did in air? What's the answer to that question? What is the answer to that question? Let's see who can get this. Who's a music person here? Take a stab at it? Want to take a stab at it, music people? Would you hear the same note? Yes, you would. Why? Once a wave has been made, the frequency doesn't change. If the frequency of this wave is 384 hertz, then the frequency will always be 384 hertz, whether it's going through air, or whether it's going through water, or whether it's going through steel. The frequency will be the same, and that's what we perceive as the note, is the frequency, not the wavelength. So, yes, we will. We'll hear it a lot sooner if it's traveling through water than it is through air, but we're not going to hear it any differently. Okay, it's going to be the same note because the frequency doesn't change. Hey, let's take a quick look at question number 10 now. A radio speaker generates sounds that your eardrum can detect. What does the operation of the speaker and your eardrum suggest about the nature of sound waves, and how does the nature of the medium air through which the sound travels support your assumptions? So you can see here that the radio speaker or your iPhone speaker or whatever, there's a felt material that's inside this cone in the speaker, and this felt material is going back and forth like this. Okay, back and forth, back and forth, back and forth, in the direction that the wave is traveling. The wave goes this way towards your ear, the particles go back and forth in the same direction. What does that tell you about the nature of sound waves? What kind of wave must a sound wave be? If the speaker is vibrating back and forth in the direction of motion that the particle is traveling, sorry, that the wave is traveling, what does that tell you about sound waves? What kind of wave is a sound wave? Transverse or longitudinal? You look like you're ready to give me an answer there, Mason. Longitudinal. And we know that because, well, I told you that a few minutes ago. But we also know that because the speaker produces waves by vibrating back and forth like this. The sound waves are traveling this way. It doesn't mean the air particles are traveling this way. It means that the air particle right here is going back and forth, which is hitting this one, causing it to go back and forth, which is hitting this one, causing it to go back and forth, and so on. Which is ultimately causing hitting your eardrum and causing your eardrum to go back and forth, which produces the sound in your brain. How does the nature of the medium air support your assumptions? Air is a gas, and what kind of wave do you have to have in a gas? Longitudinal wave. Right? We good? You guys okay with your quiz tomorrow now? Oh, you'll be fine. It's all good, right? You guys just saw a demonstration where we were sending a slinky wave down and encountering a boundary between two media, from one medium to another medium. There was two situations in that demonstration we just did. When the wave was going from slinky to somebody's hand, and when the wave was going from a slinky to the air. We found that it was reflected in both cases. When a wave goes from one medium to another medium, it's going to either be transmitted or it's going to be reflected. You're always going to get some of both, some transmission, some reflection. But when the two media are very different from one another, then most of it is going to be reflection. So for instance, when the wave was going from Slinky to Rutger's hand, then we found that most of it was reflected. Rutger, did you feel it, by the way, when the wave went from the Slinky to your hand? Yeah, you felt it a little bit. So some of the wave was transmitted into his hand, but you could clearly see that most of it was reflected. When the two materials are very different, most of it is reflection. When they're very similar, most of it is going to be transmission. Now, specifically, what happens when reflection takes place, when the two materials are very different? Well, the wave is going to be reflected right side up when you're going from medium that is more dense to less dense. From a more dense medium to a less dense medium. In the demonstration that you saw, when Slinky went, or when wave went from Slinky to air, we found that most of it was reflected, but most of it was reflected right side up. It was reflected inverted or upside down when it went from Slinky to Rutger's hand, when it went from less dense medium to a more dense medium. Now, the way this normally manifests itself is this. When the Slinky or whatever it is that's carrying the wave is attached, is fixed at the other end, then it's going to be reflected upside down because normally it's going to a more dense medium. If you attach a Slinky to a wall, the wave is going to reflect upside down because it's attached to the wall. It's going to a more dense medium. If it's not attached to the wall, if it's just floating in the air, then the wave is going to a less dense medium and it's going to reflect right side up. So we're going to say that it reflects right side up when there's a free end. Okay, when the Slinky or whatever it is that's carrying the wave is not attached. It's not fixed. It's reflected inverted when it's a fixed end or an attached end. Because in that case, it's normally going from a medium that's less dense to more dense. What if it strikes at an angle? What if it hits the boundary not straight on like it did in the demonstration that we just did? What if it strikes it at an angle? You guys have all seen this before, not necessarily with waves, but with particles perhaps. All of you guys have played pool at some point, or billiards at some point, right? You guys know intuitively, you don't even have to have learned this somewhere formally. You guys have learned this just with observations over the years. When you were little kids, you learned this, whether you realized it or not. There's the bumper of a pool table. And let's say there's a ball right here. That's not the one you want to hit. The white ball, the cue ball, is right here. And you, for whatever reason, want to get it around this blue one right here. You want to get it over here. What do? Well, you got a couple options. You could jump over it, right? You could kind of flip it, over that ball, okay, if you're good at it. But that's a harder shot. That's a much harder shot to make. We all know at some level that if we want to get around this blue one here with this cue ball, then we're not going to hit it like this. If we hit it like this, it's going to bounce back here somewhere. We know that, right? Where do we have to hit it? Well, we're going to hit it somewhere like this. And all of us at some level know roughly what angle we're going to have to hit it at. Because at some level, we all know the law of reflection. The law of reflection says this. The angle of incidence will equal the angle of reflection. In other words, the angle that it strikes the boundary at will be equal to the angle that it reflects off of the boundary at. So in other words, theta 1 will equal theta 2. Now, notice where we measure those angles from. We measure it from what we call a normal line. The normal line is a line that's drawn 90 degrees to the boundary, just like a normal force was drawn 90 degrees to the ground. Theta 1, as measured from the normal line, will be equal to theta 2, as measured from the normal line. In other words, the angle that it strikes the boundary at will be equal to the angle that it reflects off of the boundary at. That's for pool or billiards, but it also works for waves. Okay, when a wave bounces off of something, it will always bounce off at the exact same angle that it struck it at. Light's a wave. It's not a mechanical wave, but it's a wave. If you shine a laser beam on a mirror, okay, and you want to see the reflection of that laser beam, you want to see where that laser beam goes, it's going to bounce off at the exact same angle that it struck it at. Okay, waves behave the same way as particles do in this case. Oh, we're experts with reflection now. We know what happens when a wave hits a boundary and reflects, but there's one more thing that can happen. It can keep going. It can be transmitted. So let's talk for a second about transmission. When a wave goes from one medium to another, there's a few properties that will always change for that wave. We're not talking about reflecting upside down or anything like that. It goes through to the next medium right side up, always. But something changes. The most important thing that changes is the speed. The speed could increase, the speed could decrease. The wavelength will also change. And the direction of the wave will change as well, if, that is, it's coming in at an angle. If it comes straight in, it's not going to change direction. If it comes in at an angle, then it's going to change direction. It's called refraction when that happens. What stays the same? What property of the wave doesn't change when it goes from one medium to the other, when it transmits? The frequency. Once a wave has been made, the frequency doesn't change. I'm going to draw a little analogy on the board here to maybe help you understand this a little bit more. There's a boundary between pavement and a swamp. For whatever reason, I still haven't figured this one out yet, for whatever reason, we have soldiers marching on the pavement. Each of these X's represents a soldier. And if we look at these soldiers from above, maybe there's a helicopter or a plane, or you're just in a tall building looking from above. These soldiers all marching together look like they form a line, kind of like a wave front. These soldiers are marching straight north, straight upwards. That first soldier, a couple seconds later, is going to be up here. The second soldier is going to be here. The third soldier is going to be here. The fourth soldier here, right? Because they're all marching together, right? They're all marching in stride, so they want to stay together like that. This guy is going to be right here. Where's this guy going to be? He's right here. Why hasn't he gone as far during that time as the other guys have gone? Why is he kind of lagging behind now? He went from pavement to swamp. What happens to him when he goes from pavement to swamp? He slows down, right? His speed changes. He's gone from one medium to another. His speed has changed. Now let's look at the wavefront here. If we represent it as a wavefront, looks like this. All right, let's go a couple seconds later again. This guy's up here. This guy's up here. This guy's up here. Okay. This guy's in the swamp now. He's slowed down a little bit. This guy's definitely in the swamp. This guy's still there. Let's join them together. Looks like this. Okay, again, a couple seconds later. Now we got all but two of the guys in the swamp. They're all marching slower now. All the guys that are in the swamp, that is, are marching slower because they can't walk as fast in the swamp. What changes here when the soldiers go from one medium to another? Clearly the speed. They slow down when they go from pavement to swamp. What else changes? Well, here's the wavelength. When they slowed down, what happened to the wavelength? What happened to it? Look at it. Bigger or smaller? When they slowed down, the wavelength decreased, right? The wavelength got smaller. Direction also changed. They were going this way. Now they're going, the wavefront is going this way. So when they go from one medium pavement to another medium swamp, they change speed, they change wavelength, they change direction. Got it? What hasn't changed here? No. Well, not quite. How many waves do we have here in, let's say this took 4 seconds. Okay, how many waves do we have here in 4 seconds? 4. How many waves do we have here in 4 seconds? 4. What stays the same? The number of waves per second, which is the frequency, hasn't changed. Right? Make sense? This process of the bending of the wave is called refraction. Now, we're going to deal with that mathematically in Physics 30. We won't in Physics 20. Just to say that waves will change speed when they go from one medium to another. They will change direction. They will change wavelength. When they hit a boundary and reflect, they're going to reflect either upside down or right side up. When they hit a boundary and keep going, they're going to go right side up, but something else is going to change. Speed, wavelength, angle. Finally, this is our last little bit here for today. When a wave hits the boundary, it can keep going or it can be reflected. Keeps going if, or at least most of it keeps going if the boundaries, the materials are very similar. It gets reflected, or at least most of it gets reflected if the materials are very different. What happens when it hits another wave, though? What happens when one wave going in one direction hits another wave going in another direction? We just saw a little demonstration where we had a slinky wave going on one side, another slinky wave coming from the other end on the same side, and we saw that we ended up getting a bigger slinky wave. We call that constructive interference. Interference of waves occurs when two waves, two or more waves hit each other and combine. Now, after they hit each other and combine, they just keep going. They don't reflect back, as we saw in the demonstration, right? They just keep going. The wave that I sent down goes through this big interference pattern and then keeps going after it's done, right? The way that I was sending in the first place. Okay, the wave that Hayden sent down interferes, and then after it's done interfering, it just keeps going the way that it was going before. So they hit each other, they combine, but only temporarily. They're combining only while they're hitting each other. And then they just keep going, doing what they were doing before. Now, there's two kinds of interference. The first kind we call constructive interference. Constructive interference occurs when two waves combine to produce a bigger wave. That bigger wave can be a bigger crest or a bigger trough. So in other words, if you have two crests hitting each other, then they'll make a bigger crest, and that's constructive interference. If two troughs hit each other, then they're going to make a bigger trough. We'll also call that constructive interference. How do we predict exactly what the pattern of interference is going to look like? Well, we use what we call the superposition principle. We draw and we add. And the addition here is the easiest addition ever. We have to be able to add numbers like 3 plus 2. If it's a really tough one, 3 plus 2. If it's an easy one, it's more like 1 plus 1. You can see in the diagram that you see up on the board now and the handout that I just gave you, we have two waves here, two crests. We know that we're going to get constructive interference here because we know that two crests always produce a bigger crest, constructive interference. But what exactly is that crest going to look like, that interference pattern going to look like? What you want to do is take a look at both waves, both crests, as they're at this particular spot, and we want to add them together algebraically. the first wave here, right now, okay, for the first few blocks here, all we have is the one wave. So the addition is, there is no addition. If you add 1 plus 0, it's 1. 6 plus 0 is 6. Right here, it's the one wave at the natural or equilibrium position. Right here, there's nothing to add to it. So the waveform is going to be formed wherever the one wave is. Now, take a look at the next one, though. The next one, we have one wave that's 2 blocks above the x-axis. And we have another wave that's 1 block above the x-axis. 2 plus 1 is equal to what? 3. So we're going to draw a little x 3 blocks above the x-axis. Okay, the first one is 2 above. The second one is 1 above. It's going to be 3 above. Go to the next block. The first wave is 2 above. The second wave is also 2 above. 2 plus 2 is 4 above. Next one we have 2 above, 2.5 above. Add those together, it gives me 4.5 above. Next one, it's almost 2 and almost 3. It's going to be almost 5 above. 3 above, 1.5 above, 4.5. 3 and a bit, 1.5. It's about 4.5. 3 blocks above, or just over 3 blocks above. 1 block above, or just a bit over 1. It's going to be just a bit over 4. 3 plus 1 is 4. It's a bit over 4. This one is about 3.5 blocks above. About a half a block above. It's going to give me about 4 blocks above. Now what do we get right here? Nothing to add to it, right? It's just the one wave. So we just trace out the one wave. What does the wave look like at this moment when the two waves are passing each other? What we would see would be this red line here. Now that's only going to appear for a very, very brief moment in time. Because if the wave is traveling, okay, the waves are going to be at 2 different positions a half a second later. It's going to give me a different pattern. But if we were to take a snapshot in time, this is what the wave would look like. Okay, it's a bigger wave. It's constructive interference because it's a bigger wave. We'd get the same thing if we had a bigger, two troughs hitting each other. It would just be a bigger trough instead of a bigger crest. Yeah.
Would it have that little dip before it goes back?
Say that again?
Would it have that dip before it goes back to what would it?
I'm not sure which dip you're talking about. Would it have that little dip?
Like,
Do you want to come up and show me here?
would it go like this? Would it go more like this?
Fraser's saying, would it go more like this? Or would it go more like this?
Yeah.
Okay. Let's see here, Fraser. I'm not sure, actually. We'd have to draw it out. Okay? We'd have to draw it out. And we could do that fairly easily, but we'd have to have some graph paper and draw these two waves in exactly the same way they're drawn, but in different positions. So in other words, stretch this one further out this way, stretch this one further out this way, so that they were in different positions. Okay? I'm not actually sure. I'm having trouble visualizing what it would actually look like there without actually moving them and plotting them. If the two of them were completely overlapping, yes. If the two of them were completely overlapping, one was here, then what would we end up with? Something like that was nice and uniform, right? Which would happen at a particular moment in time, but again, only for a brief moment in time, just like this one would. Take a look at the next one. This is the last thing that we want to do today. This is where we have a crest and we have a trough. Let's do the same thing here. There's nothing to interfere right now. Now we have 2 above and 1 below. What do they combine to give me? 1 above, yeah. 2 plus negative 1 gives me plus 1. 2 above and 2 below give me 0. 2 plus negative 2 is 0. 2 above, 2.5 below. 2 plus negative 2.5 gives me negative 0.5. 2 above, 3 below gives me negative 1. 1.5 above, 3-ish below, negative 1.5. 1.5 above plus 1.5, negative 3.5 gives me neg 2. 1 above 3.5, negative 2.5. A half a block above 3.5 below gives me 3 below. And then, of course, we're back to the 1 wave because there's nothing to interfere with it here now. What's the wave going to look like at that particular moment in time? Something like this. Right, Hayden? What do we call that again? Constructive or destructive? Destructive. We just made a smaller wave. Destructive interference, when a crest meets a trough and we get smaller waves produced. Sometimes we get complete destructive interference. If we had a wave that looked like this, and we had a wave that looked like this, what would we end up getting? This. No wave. There would be no wave at all. How many people have noise-canceling headphones? I bought a pair of Sony noise-canceling headphones a year or 2 ago just to fly with. I didn't find them very good, actually. Okay. I tried some Bose ones once, and they were great, but that's the difference between $70 and $300, right? Noise-canceling headphones work on exactly this principle. Okay, what happens is this. Okay, you hear, there's a sound produced, right? There's a sound produced from the outside. Well, we don't want to hear that when we're listening to music or listening to the radio or whatever it is that we're listening to with our headphones. We don't want to hear the outside sound, but it's there. Now, you can have earphones that kind of cover up your ears and shield your ears somewhat from these outside sounds, but never completely. So what a noise canceling, hold on one second, guys. What a noise canceling headphone does is actually detects that sound, and it reproduces that sound. Okay, it makes that sound again, and it makes it out of phase just a little bit, so that instead of having the crest or the compression of a wave striking your ear, the compression or the rarefaction of a wave from the outside striking your ear, what they do is match up a compression from the outside with a rarefaction. And what happens then? We get destructive interference, the sound disappears. So they're actually making the sound disappear by putting 2 sounds into the headphone. Does that make sense? Putting 2 sounds out of phase with each other so that they destructively interfere. Okay, that's it for today, guys. Remember, West Ed assignments due on Friday. Okay. If you don't have any homework tonight, you might as well work on that stuff tonight. Okay? Have a good night, everyone.